In our last class, we studied some introduction to curvilinear coordinates. Wow. Here, U1, U2, and U3 are curvilinear coordinates, and the surfaces given by U1 equal to constant, U2 equal to constant, and U3 equal to constant. These surfaces are called coordinate surfaces. And each pair of these surfaces, they intersect in curves, and these curves are called coordinate curves. If the coordinate surfaces they intersect at right angles to each other, then the curvilinear coordinate system is called orthogonal curvilinear coordinate system. This is what we discussed in the last class. And then we also discussed unit vectors, unit vectors in the curvilinear coordinate systems. And how was the unit vector obtained? At the point P, what are the unit vectors in the of the curves U1, U2, and U3? U1, U2, U3 unit vectors into at the point P. How do we find them? We find them by drawing tangents to the curves at the point P, and along this tangent, if I take a unit vector, that is, if I take a vector along the tangent with magnitude 1, then these are the unit vectors along curves U1, U2, and U3. And it is given by the unit vector along the curve U1 is given by the tangent divided by the magnitude of the tangent to the U1 curve. You see, the magnitude of the tangent, it is represented by the symbol H. So H1 represents the length of the tangent del R by del U1. That is, H1 represents the length of the tangent to the curve U1 at the point P. Similarly, H2 represents the length of the tangent at the point P to the curve U2, and H3 represents the length of the tangent to the U3 curve at the point P. And this H1, H2, H3, these three quantities are called scale factors. And then we discuss one example in 2 dimensions. We use the polar coordinate systems represented by rho and phi, and we saw that the unit vectors E rho and E phi, they are different at different locations. At the point P, E rho points along this direction, E phi points along this direction, whereas at another point Q, E rho points along this direction and E phi points along this direction. So this means that for the polar coordinate system, the unit vectors are different at different points. This is unlike the I cap, j cap, and k cap unit vectors of the Cartesian coordinate system. And then I ask you to find the following. Draw the curves, rho equal to C1 and phi equal to C2. As homework, rho equal to C1. Rho equal to C1 is actually a circle of radius rho, of radius C1, and phi equal to C2. This is actually a line which is inclined at an angle phi to the x-axis. Then, as another homework, I asked you to draw the surfaces of r equal to constant, theta equal to constant, phi equal to constant. R equal to constant surface, this surface corresponds to a sphere of radius C1. Theta equal to constant, this represents cone with angle theta, and phi equal to constant, this corresponds to a plane which is inclined at an angle phi to the x-axis. Then today we are going to discuss another unit vector. So we're going to discuss another unit vector, and let me come back to this diagram again. Here U1 equal to C1, U2 equal to C2, U3 equal to C3. These are the three coordinate surfaces. At the point P, the unit vector E1. At the point P, the unit vector E1 is this. This is the unit vector E1. This is tangent to the curve U1. Similarly, the unit vector E2 is along this direction. This is tangent to the curve U2. And the unit vector along U3 will be the tangent to this curve. These three are E1, E2, E3. These are the unit vectors. We can construct another set of unit vectors at the point P. Construct the at the point P. At the point P, let us draw a normal to the surface U1 equal to C1. U1 equal to C1 surface. Surface is the perpendicular over vector over at the point P. At the point P, draw a vector which is normal to this surface. Let that vector be given by this vector. Sigi vector say this is a vector which is normal to the U1 equal to C1 surface at the point P. Adudi normal to a surface the kalina pini. Normal to a surface the kalina pini. Normal to a surface the gradient no pini go. So shall I say since we got since gradient of U1 is a vector at the point P normal to the surface U1 equal to C1 U1 equal to C1 comma a unit vector in this direction is given by capital E1 correlation. Capital E1 is equal to the gradient at the gradient of U1 divided by its magnitude. Gradient of U1 magnitude. We'll stop. So let me explain this once again. Sigi U1 equal to some constant C1. High surface is Sigi surface in Sigi surface and a vector normal to this surface is given by gradient of U1. Gradient of U1 this will give you a vector which is normal to this surface. So at the point P, at this point P, let us construct a vector which is normal to this surface and that is given by gradient of U1. And if you want to reduce this to a unit vector, what will you do? To reduce any vector to a unit vector, what do? We simply divide the vector by its magnitude. So gradient U1 by magnitude of gradient U1 will give you a unit vector capital E1 cap, which points along the direction of this normal to the plane and normal to the surface at the point P. Similarly, the unit vectors. Similarly, the unit vectors E2 head, which is given by gradient of U2 divided by the modulus of gradient of U2, and E3, which is given by gradient of U3 divided by the magnitude of gradient of U3 at P are normal to the surfaces U2 equal to C2 and U3 equal to C3 respectively. Full stop. So what have we done here? earlier earlier at the point P, we constructed 3 unit vectors. And how were these 3 unit vectors constructed? These 3 unit vectors were constructed by drawing tangents to the U1 curve, U2 curve, U3 curve. Tangent yaga unit vector ahum semgiba pamangiduna. Hojiksina amuk at the same point P, akoina unit vector ahum amuk kamaina amuk semba by drawing normal to the 3 surfaces. U1 equal to constant surface and normal at the point P, the U2 equal to constant surface theta. We draw another normal here. This is E2, capital E2. U3 equal to C3 higher surface, another normal language. So by drawing normals to the 3 surfaces at the point P, we can construct another set of unit vectors, and these 3 sets of these 3 unit vectors are given by E1, which is gradient of U1 divided by its magnitude, E2, capital E2, which is gradient of U2 divided by its magnitude, and E3, which is gradient of U3 divided by its magnitude. And these 3 gradients are calculated at the point P. Stop. Thus, at each point P of a curvilinear system, there exist in general 2 sets of unit vectors. 2 sets of unit vectors. 2 sets of unit vectors. Ahanbagi unit vectors nu kaino small e1, small e2, small e3. Sisna kaino small e1, small e2, small e3. Sisna kaino they are tangent to the coordinate curves. Tangent to the coordinate curves. And atopo setuna kaino, and second setuna kaino, capital E1 cap, capital E2 head, capital E3 head. Motion kaino normal to the normal have the perpendicular have nika normal to the coordinate surfaces. Coordinate surfaces. So let me repeat. At each point P of a curvilinear coordinate system, we can in general construct 2 sets of unit vectors. E1, small e1, small e2, small e3. These are constructed by drawing tangents to the coordinate curves. And second set, capital E1, capital E2, capital E3, these are constructed by drawing normals to the coordinate surfaces at the point P. So, the sets become identical. The sets become identical if and only if. Identical. If and only if the curvilinear coordinate system is orthogonal. Is orthogonal. Stop. Both sets are analogous to the I hat, j hat, k hat. I hat, j hat, k hat unit vectors in rectangular coordinates. Rectangular coordinates. but are unlike them in the sense that they may change direction. In the sense that they may change directions from point to point. Directions from point to point. Point to point. Correct. In the sense that they may change directions from point to point. Correct. So, meaning, the two sets of unit vectors, small e1, small e2, small e3, capital E1, capital E2, capital E3, they become identical. Identical if the curvilinear coordinate system is orthogonal. Orthogonal curvilinear coordinate system or set an identical organelle. For example, in the rectangular Cartesian coordinate system, there is XYZ system. The three surfaces x equal to constant plane, y equal to constant plane, z equal to constant plane. The three planes are orthogonal to each other. Therefore, the XYZ coordinate system, which is the Cartesian coordinate system, is an orthogonal coordinate system. So, for the XYZ coordinate system, small e1, small e2, small e3, they are the same as capital E1, capital E2, capital E3. Small e1 ga capital E1 ga chamane, small e2 ga capital E2 ga chamane, small e3 ga capital E3 ga chamane for the XYZ coordinate system. Small e1 in Cartesian coordinate system, we call it I hat. The small e2 z hat, small e3 k hat. I hat na capital E1 so igani. J hat na capital E2 igani, k hat na capital E3 igani. In if the coordinate system is orthogonal. Both sets are analogous to the IJK unit vectors in the rectangular coordinates, but are unlike them in the sense. Amarom manare analogous unlike them. Manada Bakali, Karida Manade, a polar coordinate system, the Mamanga discussed of you. We discuss the polar coordinate system. Row 5, and we saw that at different points, the directions of E row hat, E phi hat, they change. What direction J? This unit vectors, they change from point to point. Unit vector direction J, it may change from point to point. Sigis never. Unit vectors in Z, I cap, J cap, K cap, analogous to OI, but this unit vectors, they may change directions from point to point. What direction though? From one point to another change. The way which we saw an example in polar coordinates last time. This record. Idea next up, a vector. Any vector. A vectors. A vector. Capital A. Any vector can be represented in terms of the unit base vectors or the unit vectors E1 hat, E2 hat, E3 hat, or E1 hat, E2 hat, E3 hat. In the form this capital A vector is equal to A1 E1 head plus A2 E2 head plus A3 E3 head. So this can also be written as small a1 capital E1 head plus small a2 capital E2 head plus small a3 capital E3 head. Where see a1 a2 a3 and small a1 small a2 small a3 are the respective components of the capital A vector in each system. Any vector of capital A vector, this can be written in terms of E1, E2, E3 in the following form, where A1, A2, A3 are called the components of this vector A in this system. However, same vector Z, we can also express this vector in terms of the unit vectors, capital E1, capital E2, capital E3 in this form. Small a1, small a2, small a3. Now these are the components of capital A vector in the E2 coordinate system. Okay, and what we are going to study is that we are going to study only orthogonal curvilinear coordinates. I repeat, we are going to study only orthogonal curvilinear coordinates. So in such cases, small e1 and capital E1, they would be the same. Similarly, small e2 ka capital E2 ka samanagani, and small e3 ka capital E3 ka samanagani when we consider only orthogonal coordinate systems. And since we are going to study only orthogonal coordinate systems, I will simply use small e1, small e2, and small e3. Any vector ASA, unit vectors in the express the Wusmaina, we can also express represent this capital A vector, express how represent as capital A vector in terms of the base vectors. In terms of the base vectors del r by del u1, del r by del u2, del r by del u3. Which is called which are called unitary base vectors. But are not unit vectors in general. In this case, when we are at capital A vector equal to capital C1 del R by del U1 plus capital C2 del R by del U2 plus capital C3 del R by del U3. sini sigi sini da yang si koina a vector si any a hyper vector si we can represent them in terms of the unit vectors hoji mo hari sina kaino unit vector khakta natte khoi masagi tangent vector sing do adu da ju express to we have it tangent vector sing ji moi ji koina kari kawi unitary base vector kawi unit have natte ko unitary they are called unitary base vectors adu moi gi length se in general they are not unit vectors because their magnitude may not be equal to 1. In general, their magnitude is not equal to 1. Therefore, these three vectors, which are called unitary base vectors, these are not unit vectors in general. Aduna, any vector A is unit vector represent the Usmaina, I think tangent vector ahum to the express the Yai have it. Aduna, Matang Sita Swina express Toragadi C1, C2, C3 Karikawi, where C1, C2, C3 are called the contravariant components. The contravariant components. The contravariant components of the vector A. So the C1, C2, C3 is very high contravariant components of the vector A. So how will okay. So how I am later. Next, arc length and volume. Arc length and volume maybe we can discuss some examples. Examples when we discuss ourselves. So let us discuss one example. And let me share the screen. Let me share the screen. Can you see this? Ubagamra? I think you can see this one. What is this? This is a cylindrical coordinate system. So cylindrical coordinate system. This is cylindrical coordinate system. So any point P, this P, magi XYZ coordinates labor to mina, it can also have cylindrical coordinates. And the cylindrical coordinates are rho, phi, and small z. The cylindrical coordinates are represented by rho, phi, and small z. So what is rho? First, rho rho is nothing but the perpendicular distance of this point from the z-axis. The perpendicular distance of this point from the z-axis is rho. Sigi length se z-axis tagi point si kam lap ke hai base sigi length se kono rho kaureba. And what is phi? Phi is nothing but sigi point dagi you drop a perpendicular to the xy plane. Xy plane the perpendicular ma drop tawra aduri point q tare ka. So this point q ka sigi point pg and xy plane the project to bukanda and drop to bukanda point q tare. Origin dagi point q box sigi arapaji ga z axis dagi p box arapaji ga samani ka. These are rho. And see q ziga o ziga joint or line amana. Join o and q. O is the origin of the coordinate system. O and q line amana joint or. Now the angle between this line and the x-axis is called phi. And it is measured from the x-axis. X-axis dagi horaga. So I assume measure in the anti-clockwise sense. So phi is the angle between the x-axis and the line joining the origin and point q. This is phi. And what is z? Z hypercity. Sigi point p zidagi and side z-axis the perpendicular z-axis the point where this line cuts the z axis. That is the z coordinate. Matang sidi yori z coordinate sidi aigi Cartesian coordinate system gi. I repeat, matang sidi yori z coordinate sidi aigi Cartesian coordinate system gi z to chamani ko. Chamani ko. Aduna akoina Cartesian coordinate system the PD z coordinate to cylindrical coordinate system the PD z coordinate so chamani kenari kai dano rho ga phi ga kenaba. Yaraba aduga karada some authors use r instead of rho and theta instead of phi. Like karada rho haibagi mahuta r sisinaba thengnagani phi haibagi mahuta theta sisinaba thengnagani. Adubu for our study, for our discussion, we shall use rho to represent the distance of this point from the z-axis and phi to represent the angle between the x-axis and OQ. And what is Q? Q is the point P dropped on the xy plane. Correct? I know PQ, this line PQ. PQ hariba lines in a xy plane, Q hariba points to A, and this line PQ is perpendicular to the xy plane. So PQ is the foot, Q is the foot of the perpendicular dropped from the point P on the xy plane. OQ ziga x-axis ka gimarakta leriba angle zina phi ni, aduga O dagina Q bo ki arapasina rho ni. So this is how rho, phi, and z are determined in cylindrical coordinate system. What is the relation between x, y, z and cylindrical coordinates rho, phi, and z? So let me stop sharing. Let us come back. So what are we discussing? We are discussing cylindrical coordinates. So we are discussing cylindrical coordinates, and the coordinates are rho, phi, and z. And what is the relation between x, y, z and rho, phi, z? So x is rho cos phi, y is rho sin phi, and z is equal to z. X na rho cos phi ni diagram to the let us come back to that figure and let us see again. So this length is rho. Let me use the spotlight. This length OQ ye sang was a OQ. The length of OQ is rho. OQ ye sang was rho nika. OQ sidagi, we draw a line perpendicular to the y-axis. Sorry, parallel to the y-axis. So let me try to draw a line parallel to the y-axis. So from the point Q, we draw a line which is parallel to the y-axis. And this cuts the x-axis at this point. So you point the x-axis to. So from O to this is x. From O to this, I repeat, y-axis parallel over line and it meets the x-axis here. Say the points the points this is x. Line the length of this line. This is y. And this angle is 90 degree. This angle is 90 degree. This length is y. This length is x. X ni. Y ni. 90 degree ni. Theta ni. This angle is theta. And this line. This length is rho. Rho. X equal to rho cos theta y equal to rho sin theta. Aduga ai Cartesian system do toriba z tuga sigi z sigadi chamanare. Ko sidagini ko koina x equal to rho cos theta ante sorry x equal to rho cos phi y equal to rho sin phi. Ko sini ko koina pangja. Aduna let me stop sharing. All right. So cylindrical coordinate system x, y, z, and rho phi, and z, they are related by this relation. So when munni x equal to rho cos phi is equal to x equal to rho cos phi is equal to we came across this in polar coordinates. This is our polar coordinates in 2 dimensions. This angle is phi. This the length of this line. Lines in a row. If I drop a perpendicular here, x ni. Y ni. Rho ni. So x is rho cos phi, y is rho sin phi. Aduna I polar coordinates tazu I 2-dimensional polar coordinates ta x equal to rho cos phi,